Okay. Is this mic working well? Can you hear me? Okay, great. So I want to finish off the proof the proof of the runtime bound that I stated for union find via the disjoint forest data structure. Remember we had these three claims from last time. The first claim says that if x is a root, the subtree size at x is at least 2 to the rank of x. Rank is like what the height of the subtree would have been if there had been no path compressions. Claim 2 says if you follow a parent pointer, the rank strictly increases. So the rank of your parent is strictly more than your rank. Claim 3 says is a bound on the number of elements that can have high rank. If your rank is exactly k, that shouldn't say 2 to the k, it should say n over 2 to the k. The number of elements that can have rank exactly k is bounded by n over 2 to the k. So in particular, no one can have rank bigger than log base 2 of n, right? Because n over 2 to the log n is 1. If you make k bigger than that, there's less than one person who has that rank. And I realized when someone asked me a question after lecture that what I said before as to the proof might have been confusing, so I just want to say something very succinct that hopefully will clarify. Remember, the way we proved claim 3 was we said, well, let's just look at all the people who have rank exactly k. Like, for example, two people, x and y, who have rank exactly k. When x became rank k, he was the root of some tree. When y became rank k, he was the root of some tree. These trees existed at different points in time. Without loss of generality, x became rank k first. And the point is that these trees are big. We know by claim 1 that they have size at least 2 to the k. And they're disjoint. And the easy way to see they're disjoint is, okay, say they're not disjoint. So there's some z which is in both trees. Okay? What does that mean? That means that z is in x's set. Right? Remember, we're doing union find. We're maintaining a disjoint collection of sets. So at this point in time, z is in x's set. And then later, if z is in this tree, that means later z is in y's set. Right? But that means that z, x, and y are all in the same set together at this point in time. And if they're all in the same set together, that means x has to be in this tree. But that violates claim 2. Why? Because at this point in time, the rank of y is exactly k, whereas the rank of x is at least k. Right? Because it became rank k earlier, its rank is still at least k. It might even be higher because its rank might have increased over time. We don't know. But the point is, x has to be somewhere in this tree under y. But that means that it's violating the fact that ranks strictly increase as you go up trees, as you follow parent pointers, right? So that can't happen. Okay, good. So those were the claims from last time. And then I stated a theorem that said basically we have some amortized bound on how long operations take for the disjoint forest data structure. So if you do at most m finds, at most n make sets, and at most n unions, the total runtime is at most m plus n times log star of n. And I started that analysis. I basically made this analogy with opening tabs at bars, and I said the elements of our universe 1 to n, each element of the universe will have a tab. Sometimes when we do a step in our algorithm, we'll count that as one time step. Sometimes we'll put that time step on someone's tab. And then at the end of the day, what I'm going to do is I'm going to count up all the time steps that were counted normally, plus the sizes of everyone's tab. And that will account for all the time steps that have happened. Okay? So money for me, 1 unit of money is a time step. Okay? So the first thing I said is, and this, it looks weird, but we do this because it makes the analysis work out. What are the ranks? The ranks are they're integers between 0 and log base 2 of n. We already said that no rank can be bigger than log base 2 of n. I'll partition the ranks, right? I said there's the ranks from 0 to 1, 1 to 2, 2 to 2 squared, 2 squared to 2 to the 2 to the 2, 2 to the 2 to the 2 to 2 to the 2 to the 2 to the 2, etc. Right? So basically these heights, these towers of powers of 2, where the height increases by 1 as you go to the next group. And how do I open up tabs at my bar for elements? Well, when an element becomes rank k, I'll add money to his tab. I'll add balance to his, I'll deposit some money in his bank account. Okay? And how much money will I give that element when it enters group k? I'll give it 2 to the k dollars. So I'm allowed to charge 2 to the k time steps to this element. it might not stay in group K forever, right? Because ranks go up over time. Later, at some point, it might enter the next group. When it enters the next group, I'll allocate even more money, right? And give it more money again. So I'll keep adding to its balance. So when it enters group K, I'll give it 2 to the K dollars, and then at some point, its rank might increase to 2 to the K. Then how much money will I give it? Huh? I heard someone say something. 2 to the K, right? The next group would be 2 to the K, the interval from 2 to the K to 2 to the 2 to the K. So at some point, its rank is going to increase to the end of the interval and enter the next group. When that happens, I'll give it a new bonus, write it a new check of 2 to the K dollars. Okay? So the first thing that I want to convince you of is that the total tabs of everyone combined is small. If I add up everyone's tab over all time, all the tabs combined are at most n log star n. Okay? So I'm not actually spending too much on tabs. And then I'll show you how I'm actually going to do accounting to count the time steps that are happening in the algorithm. I'll show you that I can always charge to someone's tab, and no one's tab will ever go negative. Okay? Plus, there will be some other work that I'll count straight up, which won't be that much either. Okay, so first claim is that the sum of all I from 1 to n of i's total tab is O of n log star n. So proof, first, focus on a specific point in time. Or actually, let me write it like this. I'll write it's like, so this thing, the sum over I of i's total tab is equal to the sum over I goes from 1 to n of, so I has some, at the current point in time, I has some current rank. It's in some current group. Right? So we gave it how much money? We gave it 2 to the K dollars. Let's call it 2 to the KI. We gave it 2 to the KI dollars, right? In its tab. But for it to have gotten to that rank in the first place, it had to have gone through all the previous groups, right? Everyone starts at rank 0. If item I currently has rank KI, or is currently in group KI, that means its most recent deposit into its tab was 2 to the KI. But before it entered that group, it was in the previous group. How much money did we give to it when it was in the previous group? KI, right? How much did we give it before that? Log KI. And before that, log KI. Okay? And this thing here, how many terms are here? Log star KI, right? So this part of the sum total, is at most Ki times log star Ki. I'm going to be very sloppy. I'm just going to say all these subsequent terms are at most Ki. So this whole sum is at most Ki times log star Ki, which is way, way, way less than 2 to the Ki, right? Let's say it's at most 2 to the Ki for a large enough Ki. It's at most some constant times 2 to the Ki. So I can bound this. I can just say, look, this is at most, let's say, 2 times the sum over I of 2 to the Ki. Where maybe 2 needs to be some other constant. But the fact is, this is big O of that, which means it's bounded by some constant times that. Maybe 2. Maybe I have to make it another constant. But all I'm saying here is that you can basically only focus on the last deposit into I's tab, because everything else that happened before is minuscule compared to that. Okay? And then now, I can rewrite this sum I can write 2 times the sum over I from 1 to n of 2 to the ki is equal to, let's rearrange the sum. Let's group people who have the same rank. This is equal to 2 times the sum over all possibilities for the rank. R goes from 0 to log base, of group, sorry. Of group. So how many groups are there? There are only log star n groups. So let's say k goes from 0 to log star n. This is, right, the number of groups. So what am I doing here? I'm saying so here I was summing over each item one by one. Now I'm saying let's rearrange the sum so that first we sum over all these people, then we sum over all these people, then we sum over all these people, group by group. Okay? Now, what can I say about if I have some group that looks like k up to 2 to the k? Everyone here has the same 2 to the ki, right? They have the same 2 to the k term. Okay? How many people are in this group? Okay? Oh, you look. Are people have questions? And people look a little scared to me. So I don't know. Let me say what I want to say, and then hopefully what I'm saying gets through. So right here we're just summing I from 1 to n, and here what I'm saying is let's rearrange that sum to sum over groups one at a time. So first let's sum over all the I that are in this group, the 0, 1 group. Then let's sum over all the I that are in the 1, 2 group, etc. Then everyone who's in the 2 to the 2 squared group, etc. Okay? And then sum all those contributions one at a time. And if you focus on it group by group, you get something very nice that's easy to understand. So let's look at one of the groups. Let's look at the group that goes from k to 2 to the k. Everyone here contributes 2 to the k to the sum. Everyone contributes 2 to the k times, how many people are there? Well, the number of items in the group. Right? If you focus on the sum amongst all these items, this is the contribution from that group. Now, how many items are in the group? Well, those are the items that have rank exactly k, or rank exactly k plus 1, or rank exactly k plus 2, etc. So the number of items in that group by claim 3, by claim 3, this is at most the sum over all I going from k to 2 to the k of n over 2 to the I. That's the number of items in the group. This is the same thing as n over 2 to the k times 1 plus a half plus a quarter plus etc. This is at most 2, right? So this is at most 2n over 2 to the k. Right? The total contribution to that sum of the people who are in group k is exactly 2n over 2 to the k. Or it's at most 2n over 2 to the k. Times the 2 to the k. This is the number of items. Each item contributes 2 to the k. Right? So the 2 to the k's cancel, which means the total contribution from the group is at most 2n. So this is true for every group. For every group, the total contribution of items from that group is bounded by 2n. You sum that over all groups. How many groups are there? Log star n. So this is at most 4n times log star n. Okay? Right. So that's exactly what I wanted to show. I wanted to show you that the total money put into tabs is bounded. Yep. Hopefully I can get that thing to go away. Okay. So I guess, maybe this log star n is not a function that people are often dealing with, so maybe dealing with log star n makes you nervous. But do people have questions, or does this make some sense? Yeah. The 4? Okay, let me actually just get rid of this thing because it's disturbing us. Okay, I think that worked. Where does the 4 come from? Okay, so all I said was rearrange this sum so that we sum over the two, partition the i's so that first we sum over people in the first group, then we sum over people in the next group, et cetera, et cetera. And then what I wanted to understand is what's the contribution to this sum for all the i's in a particular group? Okay? And I said if you focus on a group, like focus on this group, a group is just everyone who has a rank in some interval. So everyone who has a rank in interval k to 2 to the k is in the same group. And then I said, well, everyone in this group is contributing 2 to the k. How many people are in the group? The number of people in the group is at most 2n over 2 to the k. That was this computation. So therefore, the total contribution is the number of people times 2 to the k, which ends up being at most 2n. Right? And there was already a 2 from before because of this thing being big O of that, let's say being at most twice that, so that's the 4. I don't want to dwell too much on that. If you have questions, you can maybe ask in office hours or on Piazza or ask me offline. Okay. So let me try to continue then. We know that basically we have enough. We haven't doled out that much money. All the tabs are bounded. All the tabs combined are bounded. Now I want to show you that we can spend the money we have without going negative and pay for all our time steps. Okay. So now accounting. So the total runtime is at most some constant times. So what do we say we're doing? We said we're doing at most m finds, n make sets, and n unions, right? So a make set is definitely constant time. What does make set do? It just sets the rank to 0, and I mean it's if you look at the code, make set is doing just a constant number of lines of code. Okay? So that's n, because we're doing at most n make sets. When we do union, we're doing n unions. Now, each union does 2 finds, right? And when you do union AB, the first thing you do is find A and find B. And then you put them together. So we're really doing m finds plus 2n more finds, because each union is 2 finds. So we're doing like m plus 2n finds. If you ignore those finds and just focus on the part of the union after you do the finds, once you do the finds, union is also constant time. Because once you do the finds, you just change a few pointers and that's it. So that's plus another n for the unions, plus another m plus 2n for the finds. But then within each find, you're also doing work which is like, how many parent pointers did you follow? You remember? So in a find, you follow parent pointers until you get to the root. And then you do path compression, which again takes the same amount of time, which is like the number of nodes you touched. So plus, basically, the number of parent pointers followed during finds. Right? So this is definitely a bound on our runtime. The problem is this last thing of the number of parent pointers are ever followed during a find, it's not in terms of m and n. What is it? I don't know, right? So we're going to try to understand that quantity, the number of parent pointers that I follow. So there are 3, I want to categorize the parent pointers I follow into 3 types. Say I follow parent pointer from U to V. Type 1, V is the root of its tree. And then there's going to be 2 more types. Type 2 and 3, V is not the root. type 2, v is not the root, but v is in a different group. Than u. When I say group, again, I mean partitioning the ranks according to this partition. So it's in a different rank group. And type 3, v is in the same group. So in order to count all the different parent pointers I follow, I'll just count these 3 different types separately. I'll see how many are there of type 1, how many are there of type 2, and how many are there of type 3. And I'll add them together. That covers all possibilities. So for these two, v is not the root of its tree. So how many type 1s can there be? At most 1, okay, right? Because how does it work? When you do find, you follow parent pointers until you get to the root. So you only actually follow a pointer to the root once, namely the last parent pointer you followed. It might be 0 times if you actually called find on the root, then you didn't follow a parent pointer at all. But it's not going to be more than 1. It's either 0 or 1. So you do one type 1 parent pointer per find. How many finds are there? M plus 2n, right? 2n because of the unions. Each union does 2 finds. So there are at most m plus 2n of these. How many type 2s are there? Now, we know that by claim 2 over there, as you're following parent pointers, ranks are strictly increasing, which means the groups that you're touching are increasing. Whenever you can't go to a higher group, then go up and end up in a lower group, right? You're only going to higher and higher groups as you go up the tree. So, how many times can you cross group boundaries and move into a higher group? At most, the number of groups. How many groups are there? Log star n. Right? So per find, you can cross boundaries into groups at most log star n times. There are m plus 2n finds, so this can happen at most m plus 2n times log star n times. Okay? So these I'm paying straight up with my money. I'm not using items tabs. I'm not charging anyone's tab. Type 3, though, I will charge to people's tabs. So type 3, the way I want to argue that I can pay for it, and the way I'm going to argue that I can pay for it using someone's tab is, okay, look, I followed the parent pointer from u to v. V is not the root, and they're in the same group. I'm going to charge that to use tab. I claim that, over the course of time, I'm going to be charging to a lot of different people's tabs, right? I need to make sure that no one's tab goes negative, that we actually allocated enough money over there that everyone can pay for this. And why is that? Well, the reason is because of path compression. Okay? So I followed a parent pointer from u to v. V has a higher rank than u, right? And they're in the same group, though. Okay? But it's not the root, which means that there's going to be a path compression on u, and u is going to point to someone of even higher rank going forward. Right? After this find, u is not going to point to v anymore. U is going to point to someone even higher. Okay? So how many times can that happen where the parent keeps staying in the same group? At most, the number of people in the group. Right? So let me draw something to make sure that we're on the same page here. There's a group which is all the things from k to 2 to the k. All the ranks from k to 2 to the k, right? U right now has some rank in this group. U is right here. Okay? Right now, its parent is something else in this group, which has higher rank. So its parent is some v, which is right here. Okay? But after this find, there's going to be a path compression, and u actually is not going to point to v anymore. It's going to point to some w that's even higher rank. And then the next time we do a find, u is not going to point to that anymore. There's going to be another path compression, or maybe that's the root, and then we're not in type 3 anymore. And then we're going to point to someone even higher, and then point to someone even higher, until eventually maybe its parent is not even in the group anymore. Okay? So how many times can this happen that it keeps getting new parents that have higher and higher rank, but still in the same group as u, so that we stay in type 3? At most 2 to the k. 2 to the k minus k, in fact, because there are only 2 to the k different ranks in this interval. Okay? So that can happen to u at less than 2 to the k times. How much money does u have? That's how much money u has, right? An item in group k gets 2 to the k money. We gave it 2 to the k money. So it can afford to pay for all of this. Okay? So that's it. That's the analysis. So basically, the number of times we follow parent pointers of type 3 is at most the sum of all the tabs. And we said that the sum of all the tabs is at most n log star n. So all in all, our runtime is at most some n plus m plus something bounded by m plus O of m plus n times log star n. So that's it. Any questions? Yeah.
Has anyone found
A linear time algorithm? I'll talk about that soon. Before I talk about that, I do want to say something about another algorithm that you should know for this class, which is Prim's algorithm. Okay? So we're done with Kruskal, we're done with union find. I want to say a few words on Prim. I don't want to cover it too much in depth. I think you've seen Prim in 61B. Okay. And then I'll get to your question about, does anyone know a linear time algorithm for this problem? So Prim... So another MST algorithm is Prim's algorithm. Okay. So how did Kruskal work? Kruskal, you have some graph, right? With different edge weights. Kruskal initially just makes each vertex its own connected component. And then at every time step, basically what it's doing is, it's using it's using sorting and a data structure to do it efficiently. But at every time step, what it's doing is, of all the edges that connect different components, which one is the cheapest one, and take it. So for example, maybe this is the cheapest one, so I'll take it. And then now these two things get merged together. And then maybe next this is the cheapest one, so then these two things get merged together, etc., until I finally have everything in one connected component. And the edges that I use to do the merging are the tree edges. That's Kruskal. Okay? Prim doesn't start with everyone in its own connected component and merging. Prim starts, you give it a source to begin with. It doesn't matter what source you start it with. It can be arbitrary. You give it a source to begin with. And then at every time step, there's always going to be like one pink blob, which is the one connected component that we're growing until finally that connected component is everything. So at every time step, it's going to look at the edges that leave the pink blob So here there are 3 edges that leave the pink blob. And it's going to take the cheapest one. And it's going to throw that edge into the MST. So maybe this is the cheapest one. So then it grows the blob this way. And we take this edge into the MST. And then now there are even more edges that leave the blob. Right? These edges leave the blob, but so does this edge. This leaves the blob from here, so does this edge, and so does this edge. Right? And then it takes the cheapest edge that leaves the blob, which might be this edge, and then it adds that edge in, etc., until finally the blob is everything. That's prim. Okay? And then I don't want to belabor it because it's a prereq that you've taken 61b, and I know you've seen prim in 61b. But how do you efficiently implement this? Basically, as you might have seen in 61b and hopefully remember, you use a priority queue, a heap, a min heap, right? So for prim, what you do is keep all non-blobbed, I don't know if non-blobbed is a word, but keep all non-blobbed vertices in a min heap. What's the key for the vertex? Keyed by the weight of the cheapest edge connecting V to the blob. Right? So the point is, let's say now this is the cheapest edge that leaves the blob. So we decrease key, right? I mean, we delete min, right? So the point is, all these items right now are in the heap because they're not in the blob yet. They're not blobbed yet. So they're in the heap. And then the key for this will be the cheapest edge that connected to the blob. So it'll be one of these two, whichever one's cheaper. And the key for this will be the value of the weight of this edge, and the key for this will be the minimum of these two edges. Okay. Can you see? No? Is the laptop in the way? Right? So we delete min, which basically is telling us what's the vertex that's not in the blob yet that can be reached as cheaply as possible. Basically, what's the cheapest edge leaving the blob? Okay, that's exactly what that heap is allowing us to find quickly. We delete min, so now that thing is blobbed, it's not in the heap anymore. And then let's say it's this one. It has some edges that also are, that now should be considered, because now these edges leave the blob. Like now this edge leaves the blob. So we should use it to potentially decrease key whatever this thing's value is. Right? So every time you throw a new vertex in the blob, all the edges that leave it trigger a decreased key on the other endpoint. Because now that other endpoint has a new way to get into the blob, which might be cheaper, so you might have to decrease key. So that's prim. Okay? Since you've seen it, I don't want to spend a whole lot of time on it. I just want to remind you of what prim is. It's in the textbook if you want to look more carefully. But the point is, the runtime of prim is basically, you have to first insert all the vertices into the heap, right? So n times the time to insert. Then you have to do delete min n times, because eventually everyone needs to be put into the blob. N times the time to do a delete min. Plus, eventually, every edge will be part of a decreased key, right? Because whenever one of its endpoints is put into the blob, that endpoint is going to trigger decreased key on all the other endpoints, on all the edges that leave it. So plus m times the time it takes to do a decreased key. You've probably seen binary heaps in 61b. Binary heaps are heaps that support all these operations in log n time. So you get an overall runtime of m log n plus n log n plus n log n. So this would be O of m log n with binary heaps, which by the same way is the same as Kruskal, right? Because Kruskal you had to sort the edges, which takes m log n time. Or it equals O of m plus n log n with Fibonacci heaps. I don't think you've seen Fibonacci heaps. Is that right? Okay. And they're beyond the scope of this course. You might see them in like a graduate algorithms course. But a Fibonacci heap is an amortized data structure. It solves the same problem. It solves the priority queue problem. It's a priority queue data structure. It supports these three operations, insert, delete, min, and decrease key. The beauty of Fibonacci heaps is that decrease key is amortized constant time. Insertion is amortized constant time. Delete min is amortized log n. So that's why you get an n log n plus m. Okay. What would it, by the way, what's some evidence that it might be hard to get a heap where all these operations are constant time? If you could do that, if you could get a heap where all operations are constant time, what would that imply, for example? You could sort in linear time, right? Because one way to sort is insert all the elements into a heap, and then delete min over and over and over again, and then you would sort, right? So if you're in the comparison-based model, for example, that implies that you can't get all the operations in constant time, because otherwise you'd be able to sort in linear time, which we know is impossible. But in other models of computation, like the word RAM model, where you allow yourself to do bit tricks and things like that, you could hope to have everything in constant time. In fact, that's a major open problem. So there was a student who asked, what's the fastest that people know how to do this stuff in? So let me write that down. So let me make sure I want to attribute it to the people who came up with these algorithms. Let me make sure I say their names correctly. So let's say MST, runtimes. So we know prim with a Fibonacci heap is O of m plus n log n. There was an algorithm by Chazelle in 2000. I mentioned Bob Tarjan, who's a professor at Princeton. Chazelle is another professor at Princeton. I don't know what's going on with Princeton in this class. They keep popping up. So he had an algorithm that ran in time m times the inverse Ackermann function of mn. Right? Kruskal doesn't give you that, right? Because Kruskal has to sort the edges in the beginning. So he doesn't have to sort edges. Okay? And he can manage to get down to m times inverse Ackermann, which is pretty close to linear. Okay. Karger, Klein, and Tarjan in 1995 came up with a linear time algorithm, but it's randomized. Okay. Its expected runtime is linear. So it's a randomized algorithm. Its expected runtime is linear. So it's what's called the Las Vegas algorithm, because if you're unlucky, it might take longer. Sort of like quicksort, right? In quicksort, you pick a random pivot, and then you recurse around. You pivot around that random pivot, and then you recurse. And if you were unlucky and picked a bad pivot, it could make the algorithm slow. So it's something similar, where in expectation the runtime is linear, but it could be worse if you're unlucky. And another one is Fredman and Willard in 94 also get linear time, but they do it deterministically in what's called the word RAM model. I mentioned this when I talked about sorting, right? the comparison-based model is sort of unrealistic because it's assuming that all your algorithms allowed to do are comparisons. But in a real computer, of course, like if you have the weights of the MST as ints, you can multiply the ints. You can do bitwise XOR. You can do all kinds of crazy operations. You don't just compare the ints, right? You can use the ints as addresses into memory. You can do whatever you want. So if you allow yourself the full power of what computers can actually do with machine words, they can actually get a linear time MST algorithm, deterministically. If you really want a comparison-based algorithm, there's this paper by Petty and Ramachandran in 2000. And they get runtime, I'll just call it T of Mn. Okay, so what's their runtime? Their runtime is, I'll just read for you a sentence from their paper. We present a deterministic algorithm to find an MST of a graph with n vertices and m edges that runs in time O of T of Mn, where O of T of Mn is basically the best possible bound achievable by any comparison-based algorithm. Okay, so their runtime bound is a little weird because, basically what they're saying is our algorithm achieves the best bound possible. If you ask them, what is your bound? They say, we have no idea. Okay, so it's kind of a weird situation where they can prove that there's no better comparison-based algorithm than their algorithm, at least up to a constant factor, but they don't actually know what their algorithm's runtime is. Okay, so how do they do that? I don't know. I'm not going to say all the details of their algorithm, but at some level, at some point, it reduces to some computations on very, very, very small inputs, and then it brute force searches like all possibilities of what to do with the small inputs, and uses that to solve the original problem. So because they brute force search on the small inputs, they know they're solving the small inputs optimally, and then they can use that as part of a proof to argue that their algorithm is therefore optimal. But again, since they have to rely on competing with this brute force search, they don't know a priori what that brute force search will find. They just know that they can do it. Okay, so weird situation for this problem. Okay, so I guess one nice thing though about their bound is like every time someone makes an improvement, right? Like I guess they were the same year as Giselle, but if someone, let's say to this year, gets a new comparison-based algorithm that's actually linear time, then Petty and Ramachandran can say, we already had that, right? We had that back in 2000, even though they didn't know they had it. Okay, so that's all that we're going to talk about for MST, union find, and we're done with the whole greedy algorithm chapter of this course. And now I want to move into the next topic, which is dynamic programming, and we're going to spend the rest of today, as well as next week, Tuesday, on dynamic programming. So let's switch contexts now. So dynamic programming / memoization I'm going to first talk about it in terms of memoization. Dynamic programming is something that includes memoization, but also includes a variant of it that I'll talk about. So the idea of memoization, by the way, I like to think recursively, which is why I'm obsessed with memoization. I hate bottom-up DP, which puts me at odds with certain textbooks, with many textbooks. But I'll teach you the way that I see things. And then if you want different perspectives, you can go look at different textbooks. But at least now you get multiple perspectives. Okay. So who's heard the term memoization? You've all seen memoization. So the idea behind memoization is to, it's an optimization to recursion. So the idea is you add a lookup table to recursive code so that future calls to the function, let's say your function that you're implementing recursively is f, future calls to f with the same arguments as computed before, let's say computed on before, can return immediately by looking up the answer in the lookup table. And here, so why do I have this laptop here? When it comes to DP, I personally am just a big fan of actually seeing the code in DP. So I'm going to live code for you. Okay. Let's just hope I don't have that many bugs. Oh, crap. Oh, no. No, I don't want to do that. Okay, good. I almost turned the projector off, which would have cost us some time. Okay, great. And then let me also drop down the screen. Actually, okay. So I personally am a fan of doing this with Fibonacci first. Okay, great. So we're all familiar with Fibonacci, right? We've seen it in basically every CS class we've taken, including this one in lecture 2. So what does Fibonacci look like? So if n is less than or equal to 1, return n, else return fib n minus 1 plus fib n minus 2, right? And then we say fib 10, 55, fib 2 is 3, or 1, fib 3 is 2. So it's 0, 1, 2, 3, etc., right? So you get the next number by summing the last two. What happens if you call fib 100? It takes forever, right? So we saw this in lecture 2, that computing fib n with the vanilla recursive code basically takes time that looks a lot like the n Fibonacci number, which grows exponentially, which is why this thing is taking forever. So how do you use memoization to speed this up? So let's just clean this up. So define fib memo of n. I'm going to recreate a memory of size. How many different possible inputs can be fed into the fib function? N plus 1, because as I recurse, I start at n. I'll eventually recurse all the way down to 0, so there are n plus 1 distinct inputs. So I need a memory of size n plus 1, and then I'll return, let's call this fast fib, or fib fast. Return fib memo is some helper function of n with the memory. And then now, fib memo, what does fib memo do? It looks a lot like fib. Like this. So let's say base case, return n. But we're going to check the memory. So before we check the memory, we said else, I'll say mem n equals fib memo n minus 1 mem plus fib memo n minus 2 mem. Return mem n. We have another case here, which is if it's already in the memory, we don't need to do any work. We just return it straight from the memory. Okay? So that's memoization, right? It's exactly the same code, but before we actually do work with recursion, we just check, is it in the memory? Okay? So if it's not in the memory, then the value in the memory will be none. If it is in the memory, we return it from the memory. Otherwise, we compute the answer, put it in the memory, and then return it from the memory. Right? So now, oh, yes, thank you. That's the danger with live coding. So fib fast of 100 is now really fast. Okay? So that's memoization. Memoization is just throwing this memory on top of, it's a formula, right? Once you have the function, the recursive function, you just do this whole add a memory thing, and then add an extra elif here, and then bam, you have the memoized version of the code. Okay, so it's nothing too fancy. Then, now let's think about what's going on here. I want to tie this into something else you've seen. Can you see this board? Okay. So there are a bunch of different possible inputs here. There's n minus 1, there's n minus 2, there's n minus 3, down to 0. The answer to fib n depends. Let's pretend all of these are vertices in a graph. The answer to fib n depends on which answers? Fib n minus 1 and fib n minus 2, right? So let me draw arrows. N depends on n minus 1 and n minus 2. N minus 1 depends on n minus 2 and n minus 3. N minus 2 depends on n minus 3 and n minus 4, etc. Okay. So for any kind of recursive function, I can draw this kind of graph where the nodes correspond to different arguments that could go into the function. Okay, what can you tell me about what this graph should look like? What kind of graph is it? It's a DAG. It's a directed acyclic graph, right? It's directed because I call you. We don't necessarily call each other. And it had better be acyclic, otherwise I'll have an infinite loop in my code. Right? So these are DAGs. And let's say now I don't want to write this code recursively. I want to write it iteratively. Right? So what order should I compute the answers for the nodes in this DAG? Reverse, okay, but in general, I might have an arbitrary DAG. Is there a term that we know in this class for the order I should compute answers in this DAG so that I can actually do it bottom up? Right? Topological sort, topological sorted order. In fact, it's the reverse topological sort because if the arrows go this way, it's saying n should come before n minus 1, etc. But basically reverse the arrows and then do a topological sort. Or it's the reverse topological sort of the DAG. Okay? So in this case, 0, 1, 2, 3, 4 up to n is a reverse topological sort. That's very simple. That's very easy for us. So let's now do bottom up fib. Okay, def fib bottom up n. So now I'll again make the same memory. I'll fill in the base cases of the memory. Mem 0 equals 0, mem 1 equals 1, and then for I in range 2 n plus 1, mem I equals mem I minus 1 plus mem I minus 2. Return mem n. Fib bottom up 100. Okay, looks like the same number. Just to be sure, fib fast 1,000. Does that equal fib bottom up 1,000? If not, then I have a bug somewhere. But it works. Okay, great. Okay, so that's dynamic programming. So dynamic programming basically it can either be iterative or it can be recursive, but it's the same concept. Okay. When it's recursive, it's usually called memoization. Okay? Now, what's the advantage of the bottom-up version? In this case, both of them take linear time. If you assume that arithmetic operations are taking constant time, which they're not, we know they're not, right? That was lecture 2. But if you just count flops, both of them take linear time, and both of them use n additional memory. The nice thing about bottom-up is sometimes the DAG has structure. The computation DAG has structure, where you realize as you're processing the nodes in some order, you basically don't have to remember the past anymore because it's not relevant anymore. Right? For example, if you look at this for loop in fib bottom up, when I'm trying to compute fib mem of 5 only depends on mem of 4 and mem of 3, and mem of 2, 1, and 0 don't matter anymore. I'm never going to look at them again. Right? So basically what this means is, in the fib case, I only need to keep track of the last two elements to to keep on going with the loop. So I could do an optimization of this bottom-up DP, where I'll say fib bottom-up small space, where I only need to keep two things in my memory. So now I'll just say, first of all, the memory is of size 2. It starts off as 0 and 1. Mem of 0 is 0, mem of 1 is 1. And then what I'll say is for I in range 2 to n plus 1, I'll say the new answer is mem 0 plus mem 1. And then I want to put this in mem 1 for next time. But I don't want to clobber okay, so I want to put this in mem 1, but mem 1 is going to then get moved to mem 0 because it's two things in the past. So mem 0 now becomes mem 1, and mem 1 becomes x, and then now I return mem 1. So then now fib bottom up small space 100 is, I think, the same thing. Okay? Right? So that's one of the advantages of doing things bottom up. It's not always true, but sometimes it's true that you can save memory if you do the bottom up version. Okay? So this is dynamic programming, and what I want to do for the rest of this lecture and also on Tuesday is just show you many different examples of places where DP shows up, dynamic programming shows up. Okay? So, and I'm going to code them all. We're going to code them all together. I feel like it makes things very concrete and like you can follow what's happening when you see the code. There's nothing being hidden. I hope you agree. Okay. And the DP problems we're going to discuss are easy enough to code that I feel comfortable doing it in front of you. Okay. Okay. So what's another problem that I'm going to do with DP? So we've seen shortest paths in this class. We saw 3 algorithms. We saw breadth first search. Right? Breadth first search worked for directed graphs that were unweighted. We saw Dijkstra's, which works for directed graphs which are weighted, but the weights have to be non-negative. And then we saw Bellman-Ford, okay? Where Bellman-Ford is like anything goes. And if there's a negative cycle, it'll throw an error. Okay? Bellman-Ford, by the way, actually, we'll see that soon. Bellman-Ford actually is just yet another memoized algorithm. Okay? So you basically, you write down some recursive function, you memoize it, you switch it to bottom up, and you realize, oh, this is just Bellman-Ford. So Bellman-Ford is nothing special. Okay, I guess Bellman and Ford would not be happy hearing me say that. Okay, but Bellman-Ford is just like yet another dynamic programming algorithm. Okay, it's not anything that's too fancy. So next problem. Shortest path in a DAG. I'll say single source shortest path. Single source means just like BFS and just like Dijkstra and just like Bellman-Ford, I give you a starting vertex S, and what I want to know is what are the shortest path distances from S to other people, to everyone else. Okay? Well, I can write a recurrence. I can write some kind of... So first of all, I always recommend solving these kinds of DP problems in 3 steps. Step 1 is come up with a function that's recursive and define what it is in words. Okay, what does this function mean in words? And what input would I give to the function to get the answer for my problem? So step 1, define some recursive function in words and identify what input to call it on. Oh, step 1. And then step 2 is to figure out a recurrence for f. Right? Step 1 and 2 are kind of coupled because you want to come up with an f that has a good recurrence that you can write down. So when you come up with f, you have to always keep in mind, like, does this f have a good recurrence that I could use to compute it? Figure out a recurrence for f. And step 3, and then you're basically done. Step 3 now is just analyze the runtime and memory. Right? The memory is just like how big is that memory array, and sometimes maybe you need a 2D array, whatever you need. How much memory do I need to be able to store all these answers? Okay, so for shortest path on a DAG, actually this function f that I'm going to identify is something very simple. You can see that board, the edge of that board? No? Yes. Okay, so you all can too. We're going to code this. So we're just going to define an f where f, step 1, you can see, right? Oh, you can't see. Okay, so I guess what I can do is temporarily lift this up. So our f for shortest path in a DAG is going to be something very simple. We're starting with baby steps. So we have a fixed source s. F of t is just going to be the length of the shortest path to t, from s to t. Okay, so nothing very magical there. So for us, we're going to say f of t. So this is defining f in words. F of t is the length. So this is 1. The length of the shortest path from S to T. And then we need to write a recurrence relation. So f of t, we need base cases. Well, it's 0 if t equals s. Okay, what's another case that's a base case? What if there are no edges coming into t? Right? If t is a source itself, what's the length of the shortest path? Infinity. Basically meaning it's not possible. So infinity, if the in degree of t is 0, and otherwise it's the min over all over all edges of the form a pointing into t of the weight of the edge from a to t plus the length of the shortest path to a otherwise, right? So basically what I'm saying is, okay, if we're going from s to t, well, we have to, there's on that path, so in this case t is not s because we already handled that case. So t is not s. So this path has at least one other vertex in it. So what's the vertex in that path that was right before t? I don't know. So I'll recursively try all vertices A that have an edge into T. I'll recursively try to go there, and from there take the edge from A to T. So it's the min over all such choices. This is basically like brute force search over all ways to get into T. Okay? So now, 3, what's the memory? Well, if we do DP or memoization, we need to basically, memoize or store in memory the answers for inputs. How many different possible inputs are there? N, the number of vertices in the graph, right? The input is always a vertex. So we need only n additional memory. How about the runtime? So M, so let's try to understand why. So runtime, how about time? So I'll just write it as the sum over all vertices v of the time to get f of v, ignoring the recursion, just inside of the call to f of v. How much time does it take to get f of v? This min basically means for loop, right? You iterate over all the edges that point into v, and then you do some computation. So the total time it takes is at most some constant times the sum over all v of 1 plus the in degree of v. What's the sum over all vertices V of the integree of V? Right? So I'm saying for each vertex, count how many edges point into that vertex. Add that all up. Well, that's just counting every edge once, because every edge points into someone. Right? Every edge points into some V. So when you look at V's contribution to this sum, it's going to have all the edges in it that point into V. So this sum overall of all integrees is M. So the total runtime is M plus N. So this is M plus N. So the total runtime is linear, the additional memory is linear in the number of vertices, and we see what the recurrence relation is. Okay. So the first thing we see is if we want to code this is a for loop, right? Iterating over all the edges that point into T. But we're into T. I mean, normally in like adjacency list representation of a graph, adjacency list representation means for every vertex, we know all the edges that point out of it, right? Here we're saying for every vertex, we want to be able to iterate over all the edges that point into it. That's basically the adjacency list of the reverse graph, right? So the first thing we have to do is compute the reverse graph, and then we can run this recursive code on the reverse graph. Does that make sense? So let's code that. So first we need to, so adjacency, right? Let me erase this. Let me draw an example graph. Okay. This is vertex 0, 1, 2, 3, 4, and 5. Let me give these vertices some weights. 3, 7, 1, 11. Okay. So here's a DAG. And I might want to know, say, the shortest path from 0 to 4 or something. So let's write the adjacency list representation of this DAG. So this graph. So each edge I'm going to represent as like who it's pointing. Oh yeah, let me put that down. Good one. Right? So adjacency list representation is basically like a list of lists, right? So vertex 0 has a list, vertex 1 has a list, vertex 2 has a list. Each vertex has a list of all the edges that come out of it, right? So this is vertex 0's list. It has an edge to 1 of weight 3, and it also has an edge to 2 of weight 1. And then vertex 1's list, it has an edge to 3 of weight 7. It also has, and that's all it has. That's the only edge it has. And then vertex 2 has an edge also to 3, but of weight 11. And then vertex 4 has no edges, right? And vertex 5 also has no out edges. Does that make sense? Okay. Sorry? Oh, this is vertex 0's list, vertex 1's list, vertex 2's list. Oh, vertex 3 has an edge to 4. That's true. So it has an edge to 4 of weight 1. And this is vertex 4's list. This is vertex 5's list. Okay? So that's the graph. And then let's first just define a function that reverses the graph. So let's say the adjacency list of the reverse graph we just started as empty. So everyone has no edges for now. Okay. So that's basically everyone just has an empty list of edges. And then I'll say for I in range len of G, for each edge E in the adjacency list of vertex I, so I'm iterating over each edge that comes out of I, right? That edge goes from I to some J, which is E0, and it has some weight, which is E1. And in the reverse graph, the edge actually goes from j to I. So what I'll do is I'll say edge of j, so it goes out of j now, plus equals, I'm going to I with weight. And then I'll return the adjacency list. Okay? So let's just look at the reverse graph of G here. Right? So 0, in the reverse graph, 0 isn't pointing to anyone. 1 is pointing to 0. 2 is pointing to 0. 3 is pointing to 1 and 2. That makes sense. 4 is pointing to 3, and 5 is not pointing to anyone in the reverse graph. So now let's do the shortest path code. So it takes as input the graph, as well as the starting vertex S and where I want to go T, let's say. We said that the memory needs to be how big? N. So the memory is none times n plus 1, right? Because the vertices are labeled, or n actually, len of G. The vertices are labeled 0 up to n minus 1. And then I'll return shortest path DAG memo, sorry, that's a mouthful, of GST with the mem. Does that make sense? So let's define that. Oh, not of G. I want to feed it maybe reverse G. Right? Because the recursive code needs to work with the reverse graph so it can easily iterate over things that are coming into me. So I'll feed it the reverse graph. So now let's define shortest path DAG memo. It takes as input the reverse graph, ST, and the memory. What do we say the base cases were? One base case is that if S equals T, I return 0. Otherwise, if nothing is coming into me, if nothing is coming into T, that means in the reverse graph, nothing is coming out of me. Otherwise, if rev graph, the len of rev graph T is equal to 0, return infinity. So Python has a built-in infinity that behaves the way you think it behaves. It's bigger than everything, etc. Otherwise, if it's in the memory, return it from the memory, right? Otherwise, we can finally actually do the recursion. Otherwise, memT is equal to float infinity, and I say basically for each edge that comes into me, for each edge in rev graph T, right? So this edge looks like, so it's coming from some vertex A. So A is E0, and the weight of the edge is E1. memT is equal to the min of memT and this option. This option means shortest path, DAG, memo, rev graph, S going into A with the memory, right? Plus the weight of the edge itself, because I have to actually traverse that edge. And then return memT. Make sense? Questions? So let's now run this code. So hopefully there's no typo anywhere, which is a very real possibility. But let's look at the shortest path from 0 to 3. There are two paths here. The one is 3, 7, and one is 1, 11, right? So the shortest path is 10, the 3 plus the 7. So let's see if this code actually can find that. Shortest path, DAG, in this graph G, going from 0 to 3. Okay, of course. List object is not callable. It's complaining if len of rev graph. Oh, yeah. Rev graph is a list. It's not a function. So that's the problem. Okay, good. Now it works. Okay. What about the shortest path from 0 to 5? There's no way to get to 5. Infinity. Okay? Which is what you expect. You could ask, did I really need to do memoization here? What if I just did vanilla recursion? So let me show you a graph that would be really bad for vanilla recursion. Consider this graph. Okay. So So I basically just have these like diamonds going downward. So let's say like if there are n diamonds, the total number of vertices is going to be something like 3n plus 1. Okay? So the point is, if you just do vanilla recursion, how many ways are there to get down here to the bottom of this diamond? Exponential. Because from here, I can either go right or left. Right? I can go left or I can go right. Here I have the option of going left or I can go right, etc. Right? If I were to actually run a non-memoized version of this code on this graph, I'd be in trouble. So let me just do that as the last thing. So let's generate this graph. So def gen bad graph with n will generate bad graph with 3n plus 1 vertices. Okay, so this is time. This is this for in range 3 times n plus 1. Okay, and then let's add. Let's just add all the edges that need to be there. Let's say they all have weight 1. The weights aren't going to really affect the runtime. The runtime is going to be terrible no matter what the weights are. So for I in range n, I need to add from. Let's just call. This is vertex 0, 1, 2, 3, 4, 5, 6. 4, 5, 6, 7, 8, 9, etc. So there's the vertex with name 3 times I. So add 3 times I plus equals, it has two edges coming out of it. One goes to 3 times I plus 1 with weight 1, and the other goes to 3 times I plus 2 with weight 1. And then 3 times I plus 1 has an edge to 3 times I plus 3 with weight 1. Same thing for 3 times I plus 2. It has the same thing. And then that's it. Right? There's those 4 edges. Okay? So now let's do shortest path, DAG, from vertex. In this gen, let's make n be 5. Gen bad graph n with going from vertex 0 to vertex 3 times n. Okay? And then now let's do let's do a graph with n is 10, so we have 10 diamonds. Okay? If we do with 15 diamonds, so basically how many ways are there to get to that bottom vertex? Something like 2 to the n. So 2 to the 20 is like a million roughly. So let's do 2 to the 17, which is a little less than a million. Now let's do 2 to the 18. Let's do 2 to the, let me get rid of the memoization. Let me get rid of the memoization so it's actually slow. Okay, I was like, why is this so fast? Okay, so now 15, 17, it's getting a little slower, 18, it's working a little, 19, it's working, 20, okay, 25, okay, it's really slow, as you might imagine. Okay, but now if I do put back in that memoization, where'd it go? There it is. Oh, it's like blazingly fast. Okay, so you do need memoization for this, otherwise you would have an exponential time algorithm. So on Tuesday, I'm going to show you more problems, and also, even if you focus on this problem, you might realize, like, hey, what I want is not the length of the shortest path, but like, what is the actual shortest path? Like, what's the path? What edges do I follow? And we'll talk about how to extract that as well from DP.